Hello and welcome to the fourth part of Lesson 4. In the last part of Lesson 4, we derived the Navier-Stokes equations in incompressible form, and these are the equations of motion for an incompressible Newtonian fluid. Now, we saw that the Navier-Stokes equations are quite complex, consisting of a set of coupled, nonlinear, partial differential equations. In this video, we're going to explore a solution strategy that allows us to solve the Navier-Stokes equations for certain flow situations. Now, we're going to have to make quite a few simplifying assumptions about the nature of our flow, but we'll see that nonetheless we can gain some insight into some useful engineering problems by doing so. So, on the board here, I've put a reminder of the Navier-Stokes equations. Remember that on the left-hand side of these equations, we have terms involving acceleration, both temporal and spatial. And on the right-hand side, we've got those forces that give rise to these accelerations. And the mass here is all in the density on the left-hand side. So this is, in effect, a statement of force equals mass times acceleration, Newton's second law. Let's recap the difficulty in solving these first before we go on to describe the workflow that we're going to use for this course. Firstly, these equations are nonlinear in V. So the orange set of terms inside the white brackets on the left-hand side, inside that substantive derivative, that v dot grad v term, is where the nonlinearity lies. We have velocity dot producted with velocity gradients, which are nonlinear in velocity. So we also have, represented by this one equation, as many equations as we have directions in our coordinate system. So if we're dealing with three-dimensional space, we have three coupled partial differential equations. And remember here that this is written vectorially. V is vector, Fg is vector, grad P is vector, and del squared V is also vector. So we in effect here have three sets of coupled partial differential equations. Now, there are very few analytical solutions to the Navier-Stokes equations. More often, they're solved numerically, and that opens up the field of computational fluid dynamics, and the flow scenarios that one can solve using these equations is quite astounding, and the power of modern compute allows lots of engineering flow scenarios to be solved relatively readily and relatively quickly. However, before compute power became very powerful, analytical solutions were found to these, and there's some very simple analytical solutions that we can use that do give us insight into quite a wide variety of engineering flows, and it is those analytical solutions that we're going to discuss now and that I'm going to give examples of in the future parts of this lesson. So we're going to develop a solution strategy for some of these simpler flow scenarios, and hopefully it will allow you to see through the complexity of the Navier-Stokes equations and to get through to a final solution actually relatively swiftly. So on the board, I've just put the first step of our solution strategy. Now this first step involves removing the nonlinearity and transient effects. From an analytical standpoint, what we'd like to do is to solve some ordinary differential equations, not partial differential equations. If we can solve an ordinary differential equation, a linear ordinary differential equation, then we can do so with the mathematics toolkit that we've already got. In order to do this, we need to somehow justify eliminating the substantive derivative. We can do this in one of two ways. We discussed in the last part of this lesson how the substantive derivative is all about acceleration, both temporal acceleration, changing with time, and spatial acceleration, accelerating with a geometry. So, if the acceleration is zero, then we don't have to worry about the substantive derivative, and we only worry about those terms that involve forces and stresses. However, there's some flow scenarios that we can solve for where actually there is spatial acceleration. And so there's a second assumption we can make here that justifies eliminating the substantive derivative, and that is where the flow is non-inertial. And I'm going to look at this in some depth in a second. But the first step of our workflow is all around justifying how to get rid of the nonlinearity and how to get rid of transient effects, and that is justifying eliminating that substantive derivative. Once we've eliminated the substantive derivative, what we need to do is to identify the dominant flow direction. Where is the velocity going? how is that velocity changing. And what we can do is that we can simplify 3 sets of coupled partial differential equations to one ordinary differential equation if we can make certain assumptions about the dominant flow direction and how that dominant flow direction changes. And again, I'm going to give you more details of this in a second. The third part of our workflow is then to choose a coordinate system. So up until this point, I have kept the Navier-Stokes equations in vector form. I'm only dropping them in to the given coordinate system at step 3. This is because it's a lot easier to simplify Navier-Stokes equations in vector form because we don't have to worry about all the different expanded terms that result depending on which coordinate system that you're in. So if we can keep a physical picture of what's going on and justify simplification based on the physics of the problem, then we can quite easily get rid of parts of the physics to start with, rather than having to go through term by term by term, trying to decide whether or not a given term is 0 or non-zero. So at step 3, we choose our coordinate system, and we look at our dominant flow directions, and we write down directly those non-zero terms that remain from the Navier-Stokes equations. And this is where we take the geometry of the problem into account. The final step of our workflow is to identify boundary conditions, and we're going to talk predominantly about 2 different boundary conditions, one which I'm going to call wall-driven flow, and one that I'm going to call force-driven or pressure-driven flow. This pressure-driven flow also infers a third boundary condition that we can use, which is free surface flow, but we'll talk more about that in future parts of this lesson. So there's our 4-step workflow. Justify the flow as being steady and non-inertial, i.e. no acceleration. Justify a dominant flow direction. Choose a coordinate system and then simplify, and then drop the Navier-Stokes equations from vector form into a form specific for a coordinate system at step 3, and then identify the boundary conditions and solve the resulting ordinary differential equation. Okay, all sounds quite straightforward, so let's talk in a little more depth about each of these steps. So this first step is really important because this all regards how we justify setting that substantive derivative to 0. So let's just remind ourselves which term that is. It's the entire left-hand side of the Navier-Stokes equations as I've written them here. We've already discussed that this substantive derivative is all about quantifying acceleration. And so if we genuinely have a flow that has neither temporal acceleration nor spatial acceleration, then that term is going to be 0 anyway, which is great, which is really a nice scenario to deal with. However, there are some flow scenarios, as I've already outlined, where we do have some spatial acceleration, for example, radial flow in a cylindrical coordinate system, and we would very much like to use the Navier-Stokes equations to get a solution or an approximate solution to that scenario, so we have to make another assumption about why we can set this substantive derivative to 0. Let me talk through that assumption now. On the blackboard, I have written the non-dimensional Navier-Stokes equations. Now, I'm not going to work through in this course how we arrive at this result. The way you do is to identify groups of terms that have units similar to the parameters in the Navier-Stokes equations. So, for example, you'd find a group of terms that has units meters per second and divide all your velocities by that. You'd find groups of terms that have units of Pascal, i.e. pressure, and divide your pressure terms by that. And so if you identify these groups of terms and divide each parameter by those groups of terms, you end up with the non-dimensional Navier-Stokes equations, where V star has no units, where T star has no units, where P star has no units, and where the gradient and Laplacian operators also have no units. This is rather useful because it can really pick out some important pieces of physics for us that might otherwise be obscured in the dimensional form of the equation. And the piece of physics that this non-dimensionalization picks out is the fact that that substantive derivative, that left-hand side, is pre-multiplied in non-dimensional form by a group called the Reynolds number. Now, for those of you who have sat through fluid mechanics courses before, will probably recognize the Reynolds number and its significance. For those of you who haven't, don't worry. The Reynolds number is basically stating a ratio. The Reynolds number itself has no units, it's what we call a dimensionless group, and it's a ratio of inertial forces to viscous forces. We write the Reynolds number as rho times the length scale, which I've arbitrarily written L here, times the velocity, divided by viscosity. So if viscosity is high, the Reynolds number is very low. If viscosity is low, then the Reynolds number is typically high. So for materials of low viscosity, like water, it's very hard to get a low Reynolds number unless you're in incredibly small geometries like microfluidics. For materials that you might come across in polymer processing, where viscosities tend to be very, very high, typically Reynolds numbers will be very, very low. So if we can justify the Reynolds number as being low, we can eliminate the left-hand side of the Navier-Stokes equations. It's worth also reminding ourselves what else the Reynolds number tells us. For those of you who have sat through fluid mechanics courses before, you'll probably remember that the Reynolds number can tell us whether a flow is laminar or turbulent. If you haven't sat through fluid mechanics courses before and you're unfamiliar with this, again, don't worry. Effectively, what we want to try and do is avoid the turbulent flow regime when we're solving equations because it's very, very hard. But if the Reynolds number is less than roughly 1,500, 1,000, give or take, we can be pretty sure and very safely assured that the flow is what we call laminar, i.e. it's well behaved and it's easy to solve for. Turbulent flows are hard because you've got lots of chaotic vortex motion going on, and again the origins of that are not a subject of this particular course. Now, for polymer processing, as I've mentioned, it's quite common to get Reynolds number very, very less than 1 because viscosities, zero shear rate viscosities at least, tend to be very high. Velocities tend to be moderate to low. Length scales tend to be of order a few centimetres, and densities are around 1,000. So if you plug those rough numbers into the Reynolds number, you find you get fractional Reynolds number, 1/100th, 1/500th, something of that order. Which means that we have got good justification for assuming that the substantive derivative, the left-hand side of the Navier-Stokes equations, has very, very, very negligible contribution to the answer of the result. So this is very, very useful. So, using one or other of these justifications, non-accelerating flows or non-inertial flows, we can effectively simplify the Navier-Stokes equations to the expression I've put at the base of the blackboard. The entire left-hand side is 0, and all we're dealing with, in effect, is a force balance. So that is step 1. Let's look at step 2, identifying the dominant flow direction. What we're going to do now is draw a diagram. And diagrams are really powerful when it comes to solving fluid mechanics problems. So I'm going to draw a simple diagram of flow in between two parallel slits in a Cartesian coordinate system. So I've got the x direction running along the length and the y direction being the height between the two slits. And I'm going to say my flow is being caused by movement from a higher pressure on the left-hand side to a lower pressure on the right-hand side. The flow profile that I get for Newtonian fluid in laminar flow is parabolic, and we'll prove this in a minute. But the parabolic flow results because the fluid at the walls doesn't move. The fluid's kind of attached to the walls, and so you've got two anchor points there. The fluid in the middle of the flow doesn't feel wall effects and moves very quickly. In fact, it moves at the maximum flow velocity for this given scenario. What we can say here is that the velocity only consists of one component. It's the x direction velocity. If we consider how the x direction velocity is changing, it is just changing across the width of that gap. It only changes with y. Plates are parallel. If we look at different points in x, you're going to see exactly the same profile, so long as we're a long way away from where the flow enters the gap and we're establishing a profile. So we'll assume that our x direction velocity is just dependent on y. The pressure in this scenario only changes in x. The flow goes from a high pressure to a low pressure. As we move across the gap, we'll see that all the x direction velocities are just moving in the x direction, as we've already said, which means that if we were to draw lines that follow the flow velocity, we call these lines streamlines, these streamlines would be straight and they would be parallel. You only tend to get pressure gradients at right angles to curved streamlines. So if we were accelerating this gap flow in a circle, we would get a pressure gradient across those streamlines. But since all our streamlines are straight and parallel, there is no pressure gradient in the y direction across the gap. The only pressure gradient is in the flow direction. We also are going to assume this flow is steady, and we can see from the geometry here, there's no spatial acceleration because the geometry doesn't change as a function of length. So this is good. This is a really nice, easy set of conditions to find a solution to the Navier-Stokes for. Let's look at a slightly different scenario. Let's say, as opposed to having a nice parallel slit, what we have is a very mildly tapering geometry instead. And this might be a geometry you see in lubrication. It might be a geometry you see in polymer processing. You might have a very mildly convergent extrusion die, for example. Now, the word that's important in this step of the workflow is dominant flow direction. In the first picture that we sketched, we only had one flow direction, and of course that dominated because there was only one flow direction. In this second scenario, you could make an argument that you've got very tiny flows in the y direction because we've got a mildly converging geometry. However, the dominant flow is still in the x direction, and we can make the approximation now that the velocity only has one major component, and that's in the x direction. That major velocity component only changes in one direction, and that's in the y direction. And again, you can make some arguments as to whether you might have a very mild transverse pressure gradient, but we've only got one dominant pressure gradient, and that is in the flow direction, in the x direction. And so we can say here that really you've got negligible acceleration. So we're just going to look at the dominant flow directions, and it's effectively the same problem as we're solving at the top diagram. It's just we might want to describe how our walls change as a function of length in a slightly more detailed way. But we'll not worry about that just for now. So step 2, identify a dominant flow direction, draw yourself a diagram, and write out how the velocity changes with a coordinate, and write out which velocity that you've got, and how pressure changes with a coordinate. And we're aiming to get just one velocity component changing in one direction, and just one pressure component. Okay, so step 3, we're now going to choose our coordinate system and simplify the Navier-Stokes equations and drop them from vector form into a form that is specific to our coordinate system. So, for our infinitely wide little slit that we've had a look at, the coordinate system is Cartesian. I've chosen this because it's nice and easy. So, there is the vector form of the simplified Navier-Stokes equations, having justifiably ignored, the substantive derivative on the left-hand side. And we're just going to say, okay, our flow in the slit is horizontal. Gravity is going to be acting at 90 degrees to that and has negligible effect because I've already said my flow is unidirectional in the x direction. So the effect of gravity is negligible. It doesn't act in the flow direction. I'm going to ignore it. Fine. If I look at my pressure term, I have decided that my pressure only changes in the x direction. We've got the term there minus grad p, and we know that that is a vectorial quantity because the gradient operator is a vector. So the only non-zero part of that vector is going to be how pressure changes with x, because we've already sketched that out in our diagram. So the only gradient of pressure we have is dp by dx. I'm now going to look at that Laplacian term, and again, from my diagram, I have identified all I have is an x direction flow component. Moreover, that x direction flow component only changes in y. So, the only non-zero part of that Laplacian is going to be the second derivative of Vx with the second derivative of y. And that is all I have left of my Navier-Stokes equations. And I can just simply write them down as 0 is going to be equal to minus dp by dx plus mu d2Vx by dy squared. I can simplify it one step further as well, because I can say that, well, minus dp by dx is approximately the pressure gradient I have in my flow. So if I'm looking at a geometry, let's take the pressure drop across that geometry, d delta p, and divide that by the length of the flow direction, L. So I'm going to approximate dp by dx by delta p over L and remove that derivative. And all I have remaining is a second order ordinary differential equation that is now very straightforward to solve. The fourth step, how we solve that differential equation, involves identifying boundary conditions of our flow. So let's look at my infinitely wide parallel slit again, where my flow is in the x direction and it changes in the y direction and it's being pressure driven. What boundary conditions have we got here? Well, if we think about it, we can identify where the maximum velocity is for this flow. This flow is symmetric about its center line. So if we go halfway into that gap, our flow velocity is maximum, which means the derivative of my flow velocity with respect to y is 0, because it's a maximum and a turning point. And if we remember Newton's law of viscosity, tau equals mu dvx by dy in this case, we'll see that the shear stress is 0, which is a very useful boundary condition. I'll give you an example how to implement that in a second. So that's one boundary condition. We've got a second order ODE. We might need another boundary condition, and what we're going to do is to look at the walls. And at the walls, the fluid isn't going anywhere. There's what we call the no-slip boundary condition. So at the bottom of the slit and at the top of the slit, the velocity is 0. So with a strategic location of our axes, we can easily solve this ordinary differential equation, and we get a quadratic solution in Cartesian coordinates. Let's look at a second scenario. Let's say that I haven't got a pressure-driven flow, but I've got a flow that's being driven by a moving wall. And in this particular diagram, I've drawn the top wall to be a belt that moves. Now, as that belt moves, I'm also assuming that the fluid outside of the belt on either side is exposed to atmospheric pressure. So there's no pressure gradient here driving the flow. All we have is the motion of a belt driving the movement of the fluid. Now I know already that in Cartesian coordinates that gives me a linear velocity profile rather than a parabolic velocity profile, and again we'll prove this later on. And if we think of boundary conditions here, what have we got? Well, we know that the wall is moving, so at the top of the gap, we've got a specified x direction velocity. We know the bottom wall is stationary, so at the bottom of the gap, we've also got a specified wall velocity, it's just set to 0. So in effect, we've got two no-slip boundary conditions. At the top, the fluid is stuck to the wall, but the wall's moving. And at the bottom, the fluid's stuck to the wall, but the wall's stationary. We also have 0 pressure gradient. So if we think of the equation we're solving, we are now solving an equation where every term of grad p is 0. And so all we're solving is mu del squared v equals 0, which actually just gives us a first order ordinary differential equation. And in Cartesian coordinates, we end up with a linear solution. So let me just sum up a few points. I've gone through a workflow that gives 4 steps to simplifying the Navier-Stokes equation for certain classes of flow problem. The first step was to justify that the flow was non-accelerating. In cases where moderate spatial acceleration exists, we can fall back to a second justification for neglecting the substantive derivative, which involves how much inertia there is in the flow. If there's very little inertia in the flow, if the Reynolds number is substantively less than 1, we can also justify ignoring the substantive derivative, because in non-dimensional form, the substantive derivative is pre-multiplied by the Reynolds number. So if the Reynolds number is vanishingly small, the substantive derivative has little effect on the solution. The second step was to identify a dominant flow direction, draw a diagram, write out which velocity components you've got and how they change with a coordinate. The third step was when we simplified the Navier-Stokes equations from vector form into a chosen coordinate system. And so we chose a coordinate system that was relevant for our problem and just used the information from step 2 to identify which of the terms of the Navier-Stokes equations remained to be non-zero. The fourth and final step was to look at the flow scenario, to identify the boundary conditions, and to solve the resulting ordinary differential equation.